Hey, I'm Broderick. Welcome to part 2 of the Apex Power Design walkthrough series. Today we're going to tackle a more complicated issue, power filters for PWM amplifiers. Power design makes it easy to design and analyze these filters. Today we're going to design a filter for SA09, build it, and then compare the bench results with Power Design's predictions. Let's step back and ask, why would you need a power filter? The output of a PWM amplifier is a series of pulses, the duty cycle of which defines the output state. Many loads, like motors, don't need a filter. The motor will turn just about as smoothly with a pulse train as it will with DC voltage. However, audio applications need much better linearity. A loudspeaker won't sound very good with pulses, so we need a low-pass filter to smooth out that signal. So let's go to Power Design and select the PWM Filter Design module. Select SA09, use the maximum voltage and maximum switching frequency. For an audio application, we probably want to set our cutoff frequency above the audible spectrum. I'll put 30 kHz into cutoff frequency field. I'll skip ripple voltage for now. This field only influences the recommended filter order. Our load will be an 8 ohm speaker. And lastly, I'll set our actual filter order to 2 because, well, I already designed my board for it. Now have a look at the schematic. Up here we can toggle half bridge and full bridge filters, and even choose between 3 different types of filters. Component values are automatically calculated based on our inputs. Let's take a look at the attenuation plot. This plot assumes all of your components are perfect inductors and capacitors, so it's just what you'd expect. Minus 3 dB at the cutoff frequency, and a minus 40 dB per decade roll-off afterwards. The order of the filter changes the roll-off slope. Take a look down here. With a second order filter, we can expect 180 millivolts of ripple voltage at the load, as well as 1/3 of an amp of ripple current into those first inductors. One last thing before we switch over to the bench. Click Load Filter to Power Sheet. This takes you to another module where you can alter your filter components and see what happens when the amplifier is connected. I'm going to change these components to standard values, 33 microhenries and 470 nanofarads. And we can see that the attenuation plot does not change much. But what happens if we remove the load? We see peaking around the cutoff frequency. Now check the impedance. It drops to almost 0 ohms at 30 kHz. The amplifier is not going to be happy with that. Be very careful when testing a PWM filter unloaded. This is a very easy way to destroy it. This page can do a lot more, such as calculating heat sinks and parasitic elements in your filter components. We'll get to those in the next video. I built the filter using 2 33 microhenry ferrite core inductors and a 470 nanofarad ceramic capacitor. Our 8 ohm dummy load is connected to the outputs of the filter. Even without plugging in an amplifier, I'd like to sweep the frequency and take a look at both the transfer function and impedance on this spectrum analyzer. Here we can see the transfer function, which matches very closely with what we saw in Power Design. And here we see the impedance of the unloaded filter, which confirms that the filter resonates at the cutoff frequency. This is essentially a short circuit of your amplifier outputs, which will cause ridiculously high currents to flow and burn out the amplifier. I would highly recommend against ever testing a PWM amplifier with an unloaded filter. In the next video, we'll use Power Design to analyze the power dissipation, case temperature, and ways to improve the efficiency of the circuit. Then we'll plug in an amplifier and put those calculations to the test. After that, I'll show you how to use Power Design to close an analog loop around the system, making it more robust and precise. Thanks for watching.